Hello, dear learners, and welcome back to the Lesson BCE YouTube channel. Today, we're going to see something truly mind-bending, quantum physics. We are diving headfirst into this incredible, rule-breaking, microscopic world that behaves literally nothing like the classical physics we're used to interacting with every day. It is a realm where the impossible becomes possible, and the basic rules of reality, they are turned completely upside down.
We're kicking things off with a profound mystery that actually baffled some of the greatest minds in history. So back in 1801, a scientist named Thomas Young proved that light was a wave, demonstrating all sorts of wave-like behavior. But then, Albert Einstein comes along and shows that light is made of particles. So which is it? Is light a continuous wave, or is it a stream of distinct particles? Well, spoiler alert for the rest of this explainer, it turns out they were both right.
Here's our agenda to help us unravel this mystery today. First, what is a photon? Then, energy quantization, wave-particle duality, the de Broglie wavelength, and finally, the concept of the Heisenberg uncertainty principle. By the end of this lesson, you'll understand these basic ideas, learn the key equations, and even solve some simple numerical problems with me.
Okay, let's jump right into section 1. What is a photon? The particle of light.
So what is it? By definition, a photon is simply a discrete packet of light energy. Instead of picturing light as a continuous flowing river, think of it more like individual drops of water. This means light doesn't just flow like a wave. It also behaves like countable individual particles. And to find the energy of one of these specific packets, we use a super important equation, E equals hf. Here, E is energy, F is the frequency, and h is a special number known as Planck's constant.
And you can see this brilliantly illustrated in the photoelectric effect. Notice those red wiggly lines? They represent the photons, those distinct particles of incoming light we just talked about. They are striking a metal surface and literally physically knocking the electrons, those little gray circles with minus signs, right out of the material. This physical interaction is actual experimental proof that light behaves as a particle. Pretty cool, right?
Moving on to section 2, energy quantization. Energy comes in steps, not slopes.
This brings us to a really radical idea, first proposed by Max Planck. Energy is actually not continuous. Instead, it's transferred in specific discrete packets known as quanta. Because it's quantized in these discrete steps, the electrons and atoms can only have specific energy levels. They can't just possess any random amount of energy. They have to step up or step down in exact multiples of these energy packets. And again, it all comes back to that elegant equation, E equals hf, which shows us exactly how to calculate that energy. Which leads us perfectly into section 3, wave-particle duality. Matter can behave like waves.
The flip side of what we've been discussing is truly fascinating. Think about it. If waves of light can act like physical particles, could solid matter act like waves? The answer is a resounding yes. Particles like electrons can totally behave like waves, and waves like light can behave like particles. When an electron moves around a nucleus, it doesn't just take a simple physical path, it can actually take a wave pattern. This bizarre dual nature is a massive, key idea in quantum physics. It literally forces us to completely rethink what physical matter actually is.
To prove this mathematical reality, let's look at section 4, the de Broglie wavelength. Calculating the wave of matter.
A scientist named de Broglie proposed that, similar to light, all matter particles possess measurable wave properties, and this gives us the de Broglie equation. The formula is lambda equals h divided by p. So, the Greek letter lambda stands for wavelength, h is Planck's constant, and p is momentum, which is just mass multiplied by velocity. This equation proves that even the absolute smallest particles have real wave properties.
Let's put this into practice with a solved example. Say we want to find the wavelength of an electron with a momentum of 2 × 10⁻24 kilogram meters per second. Step 1, we identify our momentum, p. Step 2, we note Planck's constant, h, which is 6.63 × 10⁻34. And step 3, we simply plug these values into our equation, lambda equals h divided by p. So when we divide Planck's constant by that momentum, we get our solution. The math comes out to 3.315 times 10 to the negative 10 meters, meaning our final answer is exactly that, 3.3 times 10 to the negative 10 meters. It's an incredibly tiny wave, sure, but it absolutely proves that this dual nature of reality is a real thing. Okay, now it's your turn for a practice problem. A photon has a frequency of 6 times 10 to the 14 hertz. I want you to find its energy. Go ahead and use our E equals HF equation, pause this explainer to do the math, and then comment your answer down below. I'd love to see what you guys come up with.
As we get comfortable with the math, we hit Section 5, the Heisenberg uncertainty principle, the limits of what we can know.
This principle dictates the hard boundaries of what we can actually discover. Werner Heisenberg proved that it is completely impossible to know both the exact position and the exact momentum of a particle at the exact same time. Basically, the more precisely you measure where a particle is, the less precise your knowledge of its momentum becomes, and vice versa.
And this isn't just an issue with our microscopes being too weak or our measuring instruments failing us, it's a hardwired limit of nature itself, perfectly described by this mathematical inequality right here. It shows that the uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to a specific constant. Long story short, you physically cannot have perfect certainty for both.
This final concept just goes to show that the microscopic world behaves very, very differently from classical physics. Matter behaves like waves, and energy comes in distinct packets. If your head is spinning just a little bit from all of this, honestly take comfort in the words of the brilliant Nobel laureate Richard Feynman. He famously said, "I think I can safely say that nobody understands quantum physics, so we're all in good company."
But it does leave us with a massive question to ponder. If the solid, everyday objects around us are actually built from uncertain wave-like particles, what does that mean for the reality we see and touch every single day? Well, that's all for today. Keep learning and exploring physics, and don't forget to subscribe and like our channel for more lessons.